Hello viewers, welcome to our online channel. I am Dr Archana Choubey, Faculty of Science from the Bhopal School of Social Sciences. Today we will study about an important topic in organic reactions, that is electrophilic addition reactions. As we know that there are various type of reactions that take place in the organic molecules. If we broadly talk about the reactions are substitution reaction, elimination reaction, rearrangement reaction and addition reaction. In the earlier lecture, we had discussed about substitution reactions. Today, we will be discussing about addition reaction. So, let us begin. Now, when I talk about addition reaction, addition as we know, addition is adding of some parts of an atom to a molecule. And if I am talking about addition, that means there has to be some vacancy where a new atom can come and join. Therefore, addition reaction will always take place in unsaturated molecules, or we can say that addition reaction take place in alkenes, alkynes and in such molecules where there is a point of unsaturation. If we talk about the categories of addition reaction, it can be of two types, electrophilic addition reaction and nucleophilic addition reaction, depending on the type of the attacking species. If it is an electron deficient species, or we may say if it is a positively charged species which is an electrophile, then it becomes an electrophilic addition reaction, or if it is an electron excess or a negatively charged species which is termed as nucleophiles, then it is a nucleophilic addition reaction. So, today in detail we will be discussing about the first category, that is electrophilic addition reaction. As I have already said that electrophiles are electron deficient species. So, in case of, if we take the example of alkenes, we know that alkenes while looking into the structure, that an alkene has a carbon-carbon double bond. So, this point of carbon-carbon double bond is the point of unsaturation, and in case of alkenes, carbon has sp2 hybridization with a bond angle of 120 degrees which it makes with respect to the neighboring atom. So, this structure makes it quite easy for the entering species to come and attack on the electron dense population where the excess electrons are present. Now, since we are saying that pi electrons, as we have studied in the earlier topics, that the pi electrons are those which are loosely held. So, anything which is loosely held is easily available for the other species to take away. Therefore, since these pi electrons are loosely held, so they can be easily, or they are loosely held by the carbon, so they can be easily taken up by the entering electrophiles. So, the electron deficient species or the electrophiles, they feel attraction to these pi electrons and they come and attack over it. So, here as we can see in the given reaction that the bond angle which is there between the carbon and the neighboring atoms is 120. So, which makes the structure quite open. So, the entering species which will be the positively charged species generated from the molecule, this will come and attack over here easily, resulting in the formation of our desired addition compound. Now, if we take the specific example of halogenation in ethene, like for example reaction of bromine. So, when bromine gas is bubbled in the mixture of ethene, we see that a colorless product is formed and the name of the product is 1,2-dibromoethane. So, when this 1,2-dibromoethane is formed by the addition of the bromine atom on the point of unsaturation, the mechanism, if we try to discuss, we know that bromine Br2, it is a non-polar molecule. So, actually it should dissociate as in equality, resulting in the formation of two free radicals. But in presence of the pi electrons which are there at this point of unsaturation, the bromine atom, it feels repulsion. The electrons in this bromine atom bond, they feel repulsion with the pi electrons of the carbon-carbon bond, and due to which the bromine becomes a polarized molecule and it results in formation of a partial positive charge and a partial negative charge. So, when there is a partial positive charge and a partial negative charge developed on this bromine molecule, one part acts as an electrophilic end and the other as a nucleophile. So, now this bromine attacks on the alkene carbon-carbon double bond, and this attack results in formation of such a intermediate species. As we can see over here that the bromine atom is it is breaking unequally, or we may say that heterolytic fission occurs, because the bond, when it breaks in equally among the two atoms, both the pair of electrons go equally to the two atoms, it is termed as homolytic fission, and when it is unequally distributed, it goes more towards one of the atom, resulting in formation of two dipoles, or charges are being developed. One becomes a partial positive end, other becomes a partial negative end. So, this results in due to the heterolytic fission. So, this heterolytic fission occurs in bromine, and the positive part of the bromine, this acts as the electrophile. So, this electrophile will go and attack on the carbon, resulting in formation of an intermediate. So, the other carbon gains a positive charge, and such carbon intermediates which obtain positive charge are known as carbocationic intermediates. So, such carbocationic intermediate is formed, and immediately the other negative part will come and attack on it, resulting in formation of our desired product, which is 1,2-dibromoethane. Now, similarly we can take another example of ethane. Here the attachment is of a polar molecule. Here earlier example we have taken bromine, here we are taking a hydrogen bromine, or a halogen with a hydrogen atom attached to it. So, now when this reaction occurs, since HBr is already a polar molecule, so here the break bond fission will occur as homolytic fission, heterolytic fission, resulting in formation of H plus, a proton and a Br negative anionic atom. The reaction occurs in similar way as we have seen in the first example, that the proton or the electrophile in this particular case will be generated, which goes and attacks, resulting in formation of a carbocation intermediate. Then the bromine anion will go and attack at the positive end of the carbon, resulting in formation of bromoethane. So, in both the cases we have seen that the mechanism is almost the same, but the difference is only in the first case, due to the pi electrons of the ethene, the bromine molecule, which actually does not show polarity in the normal bond fission of homolytic fission, in presence of these pi electron it undergoes heterolytic fission, resulting in formation of a partial positive end and a partial negative end. Whereas in case of HBr, the molecule easily undergoes fission and resulting in formation of H plus, the electrophilic part, which attacks in the first step, resulting in formation of a carbocation intermediate, and then the final product is formed. Now, since these both examples are case of addition of the electrophile in symmetric alkenes. Now, when I am talking about symmetric alkenes, what do we understand? Like we can see ethene over here, both the carbon have similar substitutes at the ends. It is equal on both the sides. Two hydrogen atoms are attached to each of the carbon. Now, if we take another example over here, this is an example of unsymmetric alkenes. Now, if we do a similar electrophilic addition in case of unsymmetric alkenes, what are the possible results that we may expect? Now, here as you can clearly see, HBr is the reactant which produces the desired electrophile, that is H plus, and it will attack at the point of unsaturation as it has done in the earlier example. But this propene molecule, it is not a symmetric molecule, it is unsymmetric. At the point of unsaturation, we have to see that if I give the number C1 and C2 to the carbon at which the point of unsaturation is present, C1 has two hydrogen atoms attached to it, whereas in case of C2 we may say one atom is hydrogen, whereas in place of the other atom over here we have an alkyl group attached to it. So this presence of an alkyl group causes a change in the position where the addition will occur. So there can be two possible pathways that the reaction may follow. In the first path, which I have termed as A, if that path occurs, the possibility of the attack of your electrophile can be in the position of second carbon. That means the H plus will come and add to the second carbon, resulting in formation of a carbocation intermediate, and then the bromine atom will add and we will get the product 1-bromopropane. Whereas if it follows the second pathway, that is the path of B reaction that I have shown over here, in this case the electrophile will first go and attack at carbon 1. So here the intermediate that is formed has a different nature than as it was formed in the first case, we may see. So obviously the resulting product has also changed. First case we have got 1-bromopropane, and in the second path we have got 2-bromopropane. So what do you think? Is it possible that both reactions will occur at the same rate, or one will occur and the other will do not? Actually, if the real mechanism when it was performed and studied, it was found that only 2-bromopropane, this is the product that is formed when the addition of hydrogen bromide occurs on propene, whereas 1-bromopropane is not formed. So why is it so? What is the reason behind it? So the reason can be explained on the basis of the stability of the intermediate that is being formed, that is the carbocationic intermediate. Since in our earlier classes we have studied about various reactive intermediates, and we know that carbocations, they have a order of stability. And what is the order of stability? If I talk about the carbocation, since carbocation is a species with a positive charge, that means they are electron deficient species, and if I have some deficiency, so I want that the other group, if it can fulfill my deficiency, then I will be happy and I become stable. Same is the case in these intermediates also, because the carbocation is electron deficient, and any group which can give electron to these carbocations, they will make them stable. So here if I talk about the first molecule, it is this ion is a primary carbocation, because the carbon is attached to two hydrogens and one of the hydrogen is replaced by an alkyl group. Whereas the other over here, in place of another hydrogen, we have actually two alkyl groups attached to it. So this is termed as primary carbocation, this is termed as secondary carbocation. Similarly, if it would have been carbon with all the three places having three alkyl groups, then this becomes a tertiary carbocation. So what do the alkyl groups do? We know that alkyl groups show positive inductive effect. That means they have the ability to direct the electron, or they push the electron away from themselves. So this is what we can see over here, these blue arrows representing the direction of the electron away from the alkyl group. So more these alkyl groups are attached, more will be the electrons pushed towards this electron deficient carbon, resulting in making it more and more stable, because they are trying to fulfill its deficiency. So we may say that if I talk about the order of stability of carbocation, it is simple. Tertiary carbocation is most stable, then secondary carbocation, then primary carbocation, and then comes the simple methyl carbocation. So now comes another important term, or another important fundamental, we may say, that more stable the process, if a species which is formed during a process is more stable, that particular phenomena will be the preferred pathway for a reaction, because everything in this universe, each and every reaction, every object, every organism, they want to achieve stability. Same is the case with the various reactions that take place in organic chemistry. So, any molecule will be undergoing a process where it can achieve stability. So, since we know that secondary carbocation is more stable than primary, going back to this reaction, we can see that when the hydrogen or the electrophile goes and attaches to the carbon number 1, the resulting carbocation is a secondary carbocation. Therefore, this path will be a preferred pathway and the formation of 2-bromopropane will occur. Whereas, if we can see over here, if the attack would have taken place on the second carbon, the resulting carbocation, this is a primary carbocation, and as we have already seen that secondary carbocation is more stable, therefore, this path is more preferred and 2-bromopropane is the only product that is formed by the electrophilic addition in case of propene. So, this addition is governed by a rule which was given by, and it was first observed and explained by a scientist which is known as Markovnikov's. Therefore, the rule is on his name, Markovnikov's rule. So, what does this rule states? There are two important statements. First is, we can predict the product that will be formed by the Markovnikov rule, which states that the hydrogen in the hydrogen halide, as in case of HBr, the hydrogen will attach to the carbon which has greater number of hydrogens. It will go and attach to that carbon which has greater number of hydrogen. So, we have seen that it was true in this case, the hydrogen will go and attach to that carbon which has greater number of hydrogen atom. This is one way of saying the Markovnikov's rule. The another statement is that the more electropositive of the reacting species bonds to the least highly substituted carbon of the alkene. That means where there is less substitution or less bulky groups present, or you may say more hydrogen are present, the positive part will always go and attach to that part of the carbon, resulting in formation of a more stable carbocation. So, I hope you have understood this topic of electrophilic addition reaction. We have dealt with in case of symmetric alkenes and in case of unsymmetric alkenes. The point to remember is that when we are talking about unsymmetric alkenes, the addition is governed with the Markovnikov's rule. I hope it is clear, and in the next lecture, we will continue with another few examples. Thank you.